Hello everyone. Today I will present Aura, a modal understanding and reasoning assistant. The goal of Aura is to move beyond visible-only perception and infer the full extent of objects, including the occluded parts, while also answering user questions. I will introduce the motivation, the model design, the new dataset we built, and the main results. In climate monitoring, cloud cover hides important land features, such as rivers, croplands, and urban areas. If we only rely on visible pixels, analysis becomes incomplete or biased. Amodal reasoning segmentation allows a model to answer questions about risks while also recovering hidden regions, which is crucial for reliable environmental and weather studies. In a climate example, Aura receives an image and a question. It reasons about factors like flooding risk, provides a textual answer, and outputs two masks per object, one for visible regions and one for the amodal full extent. The answer explains why certain regions are important, while the masks indicate exactly where they are, including the occluded parts. This makes the inference process transparent and more useful for downstream climate modeling. Aura also generalizes to everyday images. People often ask questions such as, which objects are easy to spill, without naming a specific item. The model first identifies the relevant objects, then predicts both visible and amodal masks. This ability is important for assistive agents and robots, which need to understand objects completely, even when parts are hidden behind others. The architecture has three main components. First, a vision backbone and a multimodal LLM generate an answer with special SEG tokens marking objects. Second, a prompt encoder converts each token into an embedding. Third, two decoders predict visible and amodal masks in parallel. To model occlusion explicitly, we add two modules: the occlusion condition encoder, which estimates how much of an object is hidden, and the spatial occlusion encoder, which ensures consistency between visible and amodal masks. Together, these components allow stable reasoning and segmentation under occlusion. To train and evaluate this task, we created Amodal Reason Seg, containing more than 3,000 images and 35,000 question-answer pairs. Each question may involve multiple objects, and answers include SEG tokens for segmentation. The dataset was built using VLM prompting combined with human verification, which ensures both quality and diversity. It supports evaluation of reasoning together with visible and amodal mask prediction. On Amodal Reason Seg, Aura achieves the best results for both amodal and visible segmentation. Compared to existing methods, it improves significantly in IOU scores. Ablation studies show that both the occlusion condition encoder and the spatial occlusion encoder contribute meaningfully, and LoRa fine-tuning is also essential. These results demonstrate that reasoning combined with explicit occlusion modeling provides stronger performance than visible-only or amodal-only approaches. These examples show Aura in action. Even when objects are heavily occluded, the model recovers plausible full shapes and gives textual explanations that align with the masks. This integration of reasoning and amodal segmentation is what sets Aura apart from prior methods. To conclude, we introduce the new task of Amodal reasoning segmentation, which unifies language-guided reasoning with visible and amodal mask prediction. We contribute the Amodal Reason Seg dataset with over 35,000 high-quality question-answer pairs. We propose Aura, an occlusion-aware model that achieves state-of-the-art results in both reasoning and segmentation. This work opens up applications in climate monitoring, robotics, and interactive AI, where reliable perception under occlusion is essential. Thank you very much.